was hype, I'm going to talk about double hype, fusion and AI together. I used to be in fusion. Historically, no one really cared about it until a few years ago, and now everyone is talking about it. We didn't get any applicants for like internship. Now we have so many. We have to choose our betting. So this is our group, and I work at PPL and PU together. I'll talk about fusion and how we can use AI for it. Fusion is the main source of energy in the universe and at the solar system. This is a fusion reactor running in real time. You can see it. It's a bit big for our purposes. We want a smaller one. So what do? We take that and put it in a box. So this is a this is a tokamak, a fusion reactor, where instead of using gravity to compress this, which takes a lot of mass, we use magnetic fields. So if you can compress these two suns, we don't have two suns. It's a donut. When you take a cross-section of a donut, you get two suns. So you get the sun, and you want to compress it with magnetic fields. So there's a lot of use cases. I'll talk about how we can make the operation of a reactor better by using AI. So operation of a reactor is something like this. You have some desired output. That's a lot of energy. You want maximum energy, no instabilities, no problems. And you have the actual output. Hopefully, they match the output. You don't get a disruption or anything. You don't get less energy. Your fusion plant is here. And you have some measurements. Those are your eyes. You know, these are the cameras and whatever looking into the reactor. And then you have the hammer. Hammer is what you control with. Those are the power inputs, maybe the fueling. So how can AI help in this field? First thing I'll talk about is the state of the plasma. State of the plasma is the temperature, the density, what's going on in the fusion reactor. So we write that usually like this. Y is the state, and X is the state, and Y is your measurements. So this can be the photon count on your camera as a map. But unfortunately, we want the reverse of that. We want H inverse. And the idea is given a set of Xi's and Yi's, measurements and states, how can we find the state from the measurement? So again, here is the sun. This is the core of the sun. This is the edge of the sun. And this is approximation of a reactor, fusion electricity power plant. And we will show 0 to 1. This is the center of the sun, and outside is 1. And you'll get profiles like this, like temperature going from high temperature to lower because it's cooler at the edge. So we want to find this temperature and other properties. So, okay, so first thing I'll talk about is easier. So we have these measurements. This is the reactor. You have measurements, charge exchange, recombination, et cetera, and Thomson scattering. We do some analysis, very complicated analysis, that takes the measurements and into states. Good, and this is your map. First thing you can do with AI is take this whole thing and turn it into a surrogate model that maps your inputs to your outputs, your measurements. And you say, well, okay, this is easy, surrogate, everyone does this. But there's a nice thing that you can do here. So let's say I'm running a reactor. Reactor has a problem. One of the diagnostics failed. They always fail. One of the diagnostics will have a noise increase. Well, I can have 100 diagnostics, and you can do the permutation of all possible mechanisms, and it becomes impossible to write a code that can solve this problem. But it's easier using AI. So what I do is I take this inputs, and I say, kill this, kill that, randomly do all sorts of noise addition. And if I do that, then the AI can learn this map without me writing an if-then statement of how to inverse it. So that's really nice. And the first time we turn this new real-time, it works really fast because neural nets run fast. First shot, we turned this on, Thomson scattering failed. This wasn't on purpose, it just happened. And you get Thomson scattering measures the temperature, and you get, this is the temperature distribution that you get in time. Perfect distribution. So it works. And then we said, oh, this is great. We got a bit cocky. We can produce the temperature profile without measuring temperature. How about we try this for some other things? So we said AI, multimodal, super resolution. So if I can measure things that I haven't measured with using AI, how about we try for other things? So these are a bunch of diagnostics, megahertz stuff. And I say, OK, I want to measure the temperature. And I want the megahertz Thomson, megahertz measurement, even though I can only measure this at 50 hertz. I want to do this way faster. Is it possible? So this is your inputs, all this diagnostics. Output is your temperature. And these are where all the diagnostics are. They don't see this plot, that part of the plasma that we want to measure. So how does it work? So you have these measurements in time, and these are the diagnostics. So for each diagnosis, you can map them to that time, to the temperature, and you map all of them, and then you start doing this in the middle. You say, well, if I can map them to the temperature and here, maybe I can fill in the between. And it turns out you can do this, and you can get really good results. So you can get super resolution. You probably heard of super resolution from getting 1K to 4K in an image. This is kind of like that multimodal. So, and you can see here an example of temperature measurements. They're scattered around. You're like, what's going on here? What's going on is that there's these small crashes, instabilities. And if you do the super resolution, you can see those crashes happening over in the diagnostics and in the temperature. So this is great. You're like, hey, I got megahertz temperature. What do I do with it? Well, let's see how this works. This is the first measurement, the second measurement, and I'm filling in between. And there's an instability that happens really fast. I can even capture that and see how that works. So good, I fill in the between. What do I do with it? Well, you can start looking at phenomena no one was able to see before. So we said, okay, what is the phenomena no one saw before? There's this tiny island, like a millimeter scale tiny island, you have to zoom in here, that occurs under some circumstances when you apply 3D perturbation. People say, oh, there's this island, maybe, but no one can measure it. We said, okay, can we measure this using this megahertz? We kind of get a flattening of the profile because of the island. I'm not going to show the results, but we can see that. Like, we can see, and we say, yep, this theory is correct. Even though we never measured it, we can do AI megahertz, multimodal super resolution. This is in review. So the second part is the plant. I have a reactor. It's impossible to model, like literally. It's impossible to model. How can I model this dynamics of this plant? Because there's so many things happening. There's quantum physics. There's all sorts of stuff. So here the idea is simple. I want to find the dynamics. Dynamics is this map, F, that takes me from state controls into future state. Okay, so for our purposes, for this, for this one, we're only thinking of machine learning as just finding a good fit to any function that we want. And this is what you get. So this is the beams. We put in more power, less power, and as we do that, we can run a whole shot, replay a whole shot using this dynamics model. You see the temperatures going up, density going down. You can do this. Great. So what is the point of all this? The whole point is to control. Otherwise, why do I care about it? I want to control. So here, the idea is to find this control given my measurements. And all the stuff that I found before are hopefully useful. So this is a method of doing this is reinforcement learning. Here's AlphaGo. Basically, you learn how to play the game by just feeding the game to a neural net. And we kind of try to do this with data-based model that I just showed you. And the aim here is something like this. You have the actuators. If you go too high in power, you get instability, you crash and disrupt. And it might be maybe too low is not good either. And you try to find this path, optimal path on top here. So you have all these diagnostics. These are the control actuators. You put the reinforcement learning in between to solve that problem. And we were able to do this. This is a shot where the control wasn't working. Power goes up too much by itself. It disrupts. And for the other ones, we were able to get the highest performance shots without any instabilities. And this is how it really works. So this is the fusion power, sort of, and it's going up here. We want to kind of go as high as possible, but these are the predicted boundaries at each time it's updated. And it's kind of needle going through this phase in the middle where you can avoid instabilities and still go to the highest fusion power you can. And this was, liked by NVIDIA. So everyone's talking about NVIDIA. You can't talk about it.
And paving the way towards unlimited clean energy for us all.
We killed it using AI. They wanted to use this just before the CEO gave this talk, opening remarks for the AI, the NVIDIA yearly meeting. Finally, I'll say the same thing. This is Steve Colley, director, said that Fusion is the killer app. I don't know. I can't disagree with him by his health employer. So we can use AI for Fusion to do robust state reconstruction, multimodal super resolution, finding hidden physics, and control under uncertainty. So hopefully it's helpful. Thank you.